Okay, this chapter is about nonparametric density estimation. Okay, what are these methods? So nonparametric density estimation methods provide a way of estimating densities, so the density of any random variable, without having to assume a parametric distribution. So for example, before when we did maximum likelihood, we assumed normality, or we assumed Bernoulli or Poisson, right? There's a whole family of distributions. That's one approach. But this approach is now a way of estimating densities without having to restrict it to a particular family. And in this chapter, we concentrate on methods which are called local methods, and they actually estimate the density values point by point. So you get the estimator for a density at a given point. Okay, the simplest nonparametric estimator that you've probably already used before is the histogram estimator, right? So if you estimate the density, let's see, I have a picture here. This is the histogram estimator, right? And this would be the bin width, right? And normally you look at the fraction of data that falls within the bin. Okay, so the proportion of data that lies within a bin is going, and this is just adding up the number of observations that are within this bin out of the total. That should approximately equal the density times the width of the bin. And this suggests a density estimator. So just bring H to the other side, and this is the histogram density estimator. So it's just a fraction of observations that fall within a distance of the point of estimation, and then divided by the bin size. Okay, there's a histogram. Okay, so what is the bias and variance of this estimator? So remember, for an estimator to be consistent, we want the bias to shrink to zero, if there is a bias, right? A lot of the OLS estimator was unbiased, so we didn't have a bias. But these local estimators are going to be biased, and we'll look at the conditions under which we can get the bias to go to zero. So let's look at what the bias is, okay? And there's some techniques that are used for showing these things. So, and we're going to use them over and over again, so you definitely want to get a little bit comfortable with them. Okay, so look at the expected value. So that 1 over n in the summation is going to cancel, right? Because we're assuming everything's independent, identically distributed to, well, actually just independent. Right? It doesn't have to be identically distributed because we're just doing the density at a given point. But we are going to assume it. For here, it doesn't even matter that it's independent, but when we look at the variance, it'll matter. Okay, so now the expectation of the indicator function, right? The expectation of any function of x is going to have f of x dx, where this is the density of x, right? And this is only non-zero in this interval, so you can change the limits of integration to be x0 to x0 plus h, because everywhere else it's 0. So remember, an integral is just adding things up. So we only add the terms that are not 0 here. And at this point, we want to do a Taylor expansion of f of xi around the point x naught. Okay, and this is called an exact Taylor expansion. And this x bar is in between xi and x naught. Oh, you know what? This should be just the same. It shouldn't be one bracket, one. It should just be the same, like just a regular bracket. And you probably did this before because this is called the mean value theorem in calculus. So if you look it up, this is what we're using when we do this expansion. Okay, and so now you can break it out into these terms. So this is the first term. So this doesn't depend on xi, so we can pull it out. And this integrates here to h. Okay, so this is going to be 1. And now the second term, this is the remainder term. Okay, so we want it to be f of x naught. So that's good that the leading term is f of x naught. But then we have this additional term, and this is the bias. Okay, and so we need this to go to 0 as n gets large. So we're going to look at the conditions under which we can get this to go to 0. Okay, and in studying the behavior of these estimators, we're going to use some notation which, I mean, where I learned this notation was actually in computer science classes, but I mean, it's not like super crucial to be, good at this notation, but I just use this notation. Sometimes I want you to know what it means. It's called big O and little o, okay? But in this case, it's actually, since we're dealing with random variables, it's big OP and little op, order in probability. Okay, so we say that xn is little op of hn if xn divided by hn converges in probability to 0. Okay, and it's little op of 1 if xn converges in probability by itself. And it's big OP of hn if xn divided by hn is stochastically bounded. Okay, and this is the definition of what stochastically bounded means. Okay, so it's bounded by something. So eventually it reaches an n where this ratio is bounded. So h is greater than 0. All right, so some properties. If xn is little op of 1 and yn is big OP of 1, then if you multiply them together, so remember little op means converges in probability of 0. So if you multiply them together, they converge in probability of 0. If you add them together, they're big OP of 1. If 1 is little op, then it's also big OP, because if it converges to 0, then it's also stochastically bounded. Okay, so let's get back to analyzing this term here. We're going to look at this term and look under what conditions will this term go to 0. Okay, so first we're going to assume that the first derivative is bounded. And we can, since this is adding things up, it's always going to be less or equal if we put the absolute value sign here. Okay, because this would make every term positive. Otherwise it could be some positive, some negative. So it has to be bounded by this. We'll assume this is bounded by some constant, c. Actually, this should be uppercase c to match this c. It's the same c. All right, in this, the maximum distance here is h. Okay, because it never goes further than h apart. So this is c times h squared divided by h. Okay, less or equal to that, which is big OP of h. Okay. All right, so that means that the bias, as long as we have h shrinking to 0, the bias will go to 0. Right, see, the bias is c times h, but if h shrinks to 0, then the bias goes to 0. Sometimes I put a little n. I guess I didn't do it here. But oh yeah, here. See, I put a little n sometimes just to remind ourselves that h usually depends on n. I notice here I don't have the little n, but it's the same h no matter what. Okay, so that's the bias. So under this condition, the bias goes to 0. For something to be consistent, the bias has to shrink to 0 and the variance has to shrink to 0. I mean, that would be for mean square consistency. All right, so let's look at the variance. So here we're going to use the fact it's independent. It doesn't have to be IID because we're doing everything point by point. All right, but notice there's no covariance terms, so we are using the fact that they're independent. So this 1 over n squared h squared, sum of the variances, okay, and so this n is going to cancel with one of these n squared. So we get 1 over n h squared times the variance of the indicator function here. Okay, and we're going to show under what conditions does the variance go to 0. Okay, so let's just focus. So remember that it has this out here, 1 over n squared h, or 1 over n h squared. But let's just look at this variance for now. We can write this variance as e of the indicator function squared minus e of 1 squared. This is the indicator function too. This is quantity squared. Well, the variance is always positive, and this is going to be positive because it's squared. So we're basically subtracting something here. So we know that this is going to be less than or equal to the first term. Okay, And 1 squared is always 1. So this can be less than or equal to this. Okay. Now we already analyzed this term, actually. So when we studied the bias, we showed this. 1 over h times this is equal to f of x plus big OP of h. Okay. But now that means in terms of just this expectation of the indicator function, that's going to be h times f of x naught, right? So if we assume the density is bounded by something, this is big OP of h. So the variance is going to be bounded above by c prime times n. Well, let's look back, see what we have here. We have this, right? 1 over nh squared. And now we showed that this is bounded by, let's see, bounded by h times c prime. Well, nh squared, I guess before I canceled this n before, but because it was 1 over nh squared, now we have times h, right? If you look back here. So this can be c prime over nh. Okay, so, oh, this should be big O. Big O, sorry, I have to, some of my little o's, this should be big OP of 1 over nh. Because if I would divide by 1 over nh, it would be bounded. Okay, this is big O. Okay, so consistency, you can see, I mean, don't worry, the big O, little o, that's, I'm just showing that notation. But you can see from this expression that the variance goes to 0 as nh goes to infinity. Here. So those are the 2 requirements for consistency. Okay, so the h, well here, let's just review them. So the h has to go to 0, and then nh has to go to infinity. All right, so this is an example of an estimator that's actually not root n consistent because n going to 0 is not sufficient, okay? And for consistency in mean square, we require h goes to 0 and nh goes to infinity. So this means the width of the bin has to shrink with n, but it cannot shrink too fast. So for example, h equal 1 over n would not work. But h equals 1 over n squared, or sorry, 1 over square root of n would work. Okay. 1 over n squared would also not work. Okay. So there is a range of h that satisfies. Like if h was equal to 1 over square root of n, then this would work. Okay. Now, how do you choose h? Well, one method of choosing h, which is probably one of the most popular methods, is to minimize what's called the mean squared error or the root mean squared error. This is actually the mean squared error. But anything that minimizes mean square error will also minimize the root mean squared error. Okay, so this is the bias squared plus the variance. And I've kind of, I haven't written in what these constant terms are. You know, in general, you'd also have to keep track of what the constant terms are. Like this actually the density here, derivative of density. But for now, just ignore the constant terms. Because we're just looking, how does h have to shrink with n? So you take the derivative with respect to h, and you get that the optimal choice of h is going to be a function of n to the minus 1/3. This in the mean squared error, this is the bias squared, and this is the variance. Okay, the bias is always squared because the bias could be positive or negative. So when you square it, it makes it positive. Okay. All right, it turns out that you can actually do better than the histogram estimator in terms of getting a smaller, well, you can basically change the histogram estimator in a small way that improves the performance. Okay, And the change that you can make is instead of doing the bin on one side of x naught, you can do the bin symmetrically around x naught. Okay, so do minus h and plus h. So we have symmetric bin around the point x naught. Okay, and so you can rewrite this expression here. You can rewrite in this way. Okay, this here is called a uniform kernel. And notice this is a function of xi minus x naught over h. Okay, this is what it looks like. And it satisfies the property that, well, this 0 should be under the line. So it satisfies the property that it integrates to 1. And it's symmetric. Okay, we can also use other kernel functions. So as long as they integrate to 1 and they're symmetric, they would work. Okay, so this is a different type of kernel function called the quartic kernel function. So notice that the uniform kernel function, see where you have this indicator, all observations within h of x naught get the equal weight. Whereas a quartic kernel gives more weight to observations that are close to x naught. Let's see. So these are some, you can also use a normal kernel. Okay, the normal kernel is going to be everywhere positive. It doesn't actually drop to 0. This is a quartic kernel. Like this 15/16 is needed for integrating to 1, basically. This would be the normal kernel. Okay, so let's look at the properties of this general kernel density estimator. Okay, uniform kernel, which corresponds to the histogram estimator, is a special case. It's for a particular choice of k, you would get the histogram estimator. Okay, let's look at the bias and the variance again, like we did before. Okay, but it is just going to be slightly different techniques. I mean, similar, but a little small difference here. So if we take the expectation, so this is what we're taking the expectation over this. So the 1 over n is going to cancel with the n terms. So this is the expectation. Here we can do a change of variables. So let s equal to x naught minus xi over h. ds is going to equal to minus 1 over hn. Oh, dxi. Sorry, I'm like missing, there are a couple typos. This should be ds equals minus 1 over h times dxi, because we're going to substitute in. Okay, xi, solving for xi here, is equal to x naught minus sh. Okay, when the xi is equal to minus infinity, si is equal to infinity. All right, so that means now I'm plugging these things in. So the 1 over n cancels, or the 1 over h here, let's see. Yes, so dxi is equal to minus h times ds. Okay, so we're plugging in for dxi minus h times ds, so that's why I cancel with this h. Okay, and then the limits of integration, there's a minus sign here. Oh, darn, wait, is this? This should be positive and this should be negative. And then here I switch it back to the old limits of integration. I have to fix, this should be, I think it's correct in the notes actually, I don't know, I must have copied it here. But so this should be positive and this should be minus here. Okay, and there's a minus sign out here. Now we can go back to the old limits of integration, and this will be negative and this is positive, and you get rid of the minus sign. Okay, so this is just doing a change of variables to go from here to here. Okay, I wish I could write on the screen to correct the typos, but this should be dxi is missing here, and then this should be positive and this negative up here. All right, now we can do the same thing we did before. We just do a Taylor expansion of f of x naught. okay? But here I expanded it out to more terms, mainly because I just want to show you that if we choose the kernel function in a clever way, you can actually make the bias smaller and smaller. Okay, so we're going to Taylor expand this. This is Taylor expanding out to R terms. Okay, and it writes it in a slightly different way because this is the rth derivative at x naught. Notice we're adding this and we're subtracting it here. It's the same term. Okay, and this is the remainder term. So if we choose a kernel function that has a lot of these integrals equal to 0, okay, then the bias would be the last term. Okay, let's see. This is the remainder term, and so the bias would be this. Okay. So typically, this will improve on the histogram estimator. Okay, usually in practice, we choose a k that satisfies these two things. K of s ds integrates to 1, k s s ds integrates to 0. So this requirement here is satisfied if k is symmetric. If we, in addition, required the next integral to equal 0, then because s squared is always positive, this means that k has to sometimes be negative. Okay. All right, so lastly, you can even get the bias to be smaller here if you assume like that this difference here satisfies what's called a Lipschitz condition. Okay, this kind of controls how big the variation is here. This is some bound m. Okay, then the bias you can even get to be smaller because the distance between this is h. Okay. All right, now it turns out, so the main point, I guess, to get from this is that especially this, k of s s ds, when k is symmetric, this is satisfied, okay? And then when you do this, the bias is going to be h squared instead of h. Okay. So before, when we studied the histogram estimator, the bias shrank to 0 as h goes to 0. Now it's going to be that the bias goes to 0 as h squared goes to 0. And because h is small, so think of h as like 0.1, then h squared is even smaller. So the bias is actually going to be smaller if it's h squared instead of h. Okay. And theoretically, you know, by choosing a kernel function that satisfied a lot of these moments being 0, these integrals, that would they call it killing the bias. These types of kernels are called bias reducing kernels, but in practice people don't really use them that much, and the reason is that if the kernel is negative in places, then there's a possibility to get a negative density estimate. Okay, so empirically that's a problem because nobody wants to report a negative density estimate. Okay, in theoretical work they actually use these kernels sometimes, but usually in practice, if you're doing empirical work, you would just choose a kernel that's symmetric and integrates to 1. Okay, it turns out the variance, you know, you can show the variance using similar techniques. It does not improve on the histogram estimator. Okay, so it's still going to be variance goes to 0 as nh goes to infinity. So this is something you can try to show on your own. Okay, now let's look at choice of bandwidth. Okay, so this is doing it for general, general R, where R would be like the number of moments that equals 0. Okay, so usually in practice, this is n to the minus 1/5. So this gives you the optimal rate at which H should shrink to 0 as n gets large, trading off bias and variance. Okay, now there's one interesting result, which is actually kind of a famous result, and that's that the mean squared error of non-parametric estimators is slower than for parametric estimators. Okay, so what do I mean by that? Well, consider the parametric estimator beta hat OLS that we looked at before. That has mean 0, and the variance was, x prime x inverse sigma squared, right? Well, we can put a 1 over n here, and then so that's like, let's see, that's like multiply by n, because it's n inverse inverse. So then multiply here by 1 over n. Now this goes to e of xi prime, remember? That's just some matrix. And you can see that the variance shrinks to 0, as n goes to infinity, okay? So the mean squared error is n to the minus 1. And the root mean squared error is n to the minus 1/2. That's why when we do testing, you blow this up by root n, right? So the parametric rate is n to the minus 1/2. These n's actually should be the same. This should be little n. So I was just trying to contrast it. So if now here, this mean squared error, if we put in this optimal h, plug that into here, you can derive the rate at which the mean square error goes to 0. Okay, and it's here, minus 2r over 2r plus 1. So you see that this is always going to be less than 1, right? And so the root mean squared error is always less than 1/2. Okay, so this is kind of a famous result, that the convergence rate of non-parametric estimator is always slower than for a parametric estimator. So even if you were really clever about choosing the kernel function, you could never approach the parametric rate. Okay. Well, I mean, you approach it, but you could never reach it. That's okay. So now if you want to do more than one dimension, so I just described everything for the density of one random variable. I mean, it turns out that that's not hard. You can actually just multiply these kernels together. So you have 2 bandwidths and you multiply the kernels. Typically you choose the same kernel here. You could choose different bandwidths. Like if the variables were on different scales, you might want to choose different bandwidths. But that's how you'd multiply it. But if you analyze the convergence rate of this estimator, which we're not going to do just because doing one is enough, but the convergence rate of this estimator is actually going to be n times the 2 h's multiplied together here. So the variance is going to go to 0 slower because we've got 2 h's instead of 1. Okay, so it turns out that if you have more variables, that the convergence rate of the non-parametric estimator is actually slower. Okay, so this is called the curse of dimensionality. Like the non-parametric, the rate of convergence of the estimator depends on how many variables there are. Okay, and this is something you do not see with the parametric estimator, because with the parametric estimator, even if you had 30 x's, it would still be like root n estimator. Okay, it's not that the convergence rate slows down with the number of x's. But in this case, it actually gets slower and slower if you have more variables. Okay, so that's why these methods are usually not applied for a large number of variables. I mean, there are other methods that are kind of in between non-parametric and parametric that sort of bridge the gap and help you deal with more variables. There's a whole class of like semi-parametric methods. Okay, so this is the last slide for the kernel density, the chapter on kernel density estimation.